So after studying regular languages, we showed that there are languages which are not regular language, right? And the tool we used for that was this pumping lemma for regular language. So we used this lemma to prove that certain languages are not regular language. For example, 0 to the I, 1 to the I for all I. And then we proved that this class of context-free languages, which is a strict superset of regular languages. And in fact, if we consider this 0 to the I, 1 to the I example, so if we consider 0 to the I, 1 to the I example, so this was not regular, but then we showed that this is context free. And this is how we proved that context free languages are strict superset. But now we want to go beyond. So we want to see what lies beyond context free languages. So to do that, again, we need some kind of tool to prove that some languages are not context free. So for example, we will show at the end of this video that if I take say 3 symbols, say 0, 1, 2, and if I take 2 to the I here also. So this thing, so if I take this for all I, for I in, so this natural number, so then we will see that this is not a CFL. Okay. And we will prove that using this pumping lemma for context free languages. And if you compare this with the pumping lemma for regular languages, they have a very similar structure. So what does this pumping lemma for regular languages say? So if L is a regular language, so then there exists a constant n which only depends on L. Okay. And so we call this the pumping lemma constant. So for any regular language L, we have this constant n, such that if you take some string from L which is sorry, here I should have the size of z. If the size of z is more than n, then we can write this z as UVW, such that now we can pump this part, this V, so we can have this UVIW, and this will also be in L for all I. In fact, we can reduce this V also. And we can pump this, so to in order to get larger and larger string, it is only useful if we have this, that the length of V is at least 1. And this is ensured by this lemma, that if the z is of length greater than n, then we can break this down into UVW such that this V part is non-empty. And on top of that, we also had another constraint that this UV, the length of UV is less than or equal to n, and then we can pump this part, this middle part, and all these strings will also be in L. So this was pumping lemma for regular languages, right? Now pumping lemma for context free languages again says that if a language is now CFL, so just mark the difference. So if a language is CFL, then there is a constant n like before, depending only on L, such that if I take any string in L which whose length is greater than n, then we can break this z into parts. So here the number of parts was 3, so and we were pumping this middle part, right? So here for this context free language, it says that we can break this into this 5 parts, u, v, w, x, y, such that this vx has at least one symbol, right? So it's even allowed to have one of this as empty, but if I take them together, if you take them together, then this together must have at least one symbol. Both of them cannot be empty. So, and both of them can be non-empty also, but both of them cannot be empty together. and this part is less than n. So now this two condition looks very similar to this, where yeah, and now the pumping looks like this. So here we were pumping the middle part, so here the pumping happens here and here. So it's like you have this this 5-part string, and this leftmost, rightmost, and this middle part remains as it is, and this the second part and the fourth part, so they get pumped, and all these things will also be in L. Okay, and again here you see, so in order to have a successful pumping, we need we cannot have both of this Vx as empty string. So then there is no meaning of pumping. So that is why this is useful here, that if I take together V and X, so together they has at least one symbol in them, so that I can get larger and larger string here. And also this part is less than equal to n. Okay. So this is the statement for the pumping lemma for context-free languages, and we will write this down into formal logical statement. And for that, and while discussing this pumping lemma for regular languages, we already mentioned this logical notations. You already know them, and we then again discuss this before. So I am not going through all these things once again. So just the important point is that if you have a chain of this alternating quantifiers, so for all there exists, for all there exists. So whenever you have a there exists, so this variable will depend on the previous variable. Okay. So here this y depends on x, here this w depends on the previous variables. So this dependence is there, and then when you negate, so this for all becomes there exists, and the negation comes inside. This there exists becomes for all, this negation comes inside, and we can write the negation of this AND condition, this conjunction condition, as a implication here, and similarly we can write the negation of this implication as a conjunction like this. So in all of these cases, this this negation is pushed inside in the rightward direction, even in here. So yeah, this is what we discussed before, and this is what we will use again here. So now in the in the context of the CFL, what does pumping mean? So this is what pumping now means. So we are pumping this second part and fourth part together. So just to emphasize this thing, now given any language L, so here we are not considering this L to be a CFL. So just take this as a definition of pumping. So we also defined pumping in regular language, but now we are redefining this thing. So this is what overrides the previous definition of pumping, what you learned in regular languages. This is somehow a generalized version of that. So here we are defining pumping, and this pumping depends on this parameter n. So for any language n, so you have some this integer n, and given this L and n, you take some z in L which has length more than or equal to n, and then this z can be pumped if we can break this z as this 5-part string, such that if you take together this Vx, it is not empty, and this Vwx is less than equal to n, and for all I, this pumped up version, so where we pumped the second and fourth component, so that is also in L. So take this as the definition of pumping. and this pumping depends on this L and this integer n, okay, because here the conditions involve this n, and this z has to be of length more than equal to n. So formally we can write that z can be pumped if there exists UVW xy such that z is UVW xy and Vx is not empty and the length of Vwx is less than equal to n, and for all I u v to the I w x to the I w y is in L. So this is a formal statement. So as an example we can have this. Say this is our language, and suppose we fix this n to be something. In the general proof, we won't take any specific value here. We need to prove this for all n. But here, just to demonstrate this definition, I am taking some specific value of n. Let's say it's 4. And then we take some z which is in L and whose length is more than or equal to 4. So this will do. And we argue that this can be pumped because we can break it down like this. Okay, so the first 0 is our u, then the second 0 is our v, and then this 0 1 after that, this is our w, and then x is this fourth this 1, and then y is this last one. So that means when we are pumping this 0, so this 0 and this one. Okay, so these are our v and x. So when we pump, then you see that again we get something of the form 0 to the I, 1 to the I. Now what if we choose some different decomposition? For example, u is epsilon, v is just the second 0, w is again epsilon, x is 0, and y is the rest of the thing. Okay, so then if we pump according to this breakup, say we pump it once, so it becomes 2 and 2. So then we have something like this, because both v and x are just 0 0, and this will not be in L. So does it break our definition? It doesn't break our definition because the definition said there exists. So if you can find any one breakup here, okay, you do not have to go for all breakup for this definition to satisfy. So if you can any breakup such that you can carry out this part, so then you say that this z can be pumped. But then what does it mean to say that z cannot be pumped? Now see here, this negation thing comes in practice. So if you take a negation here, then this there exists will change to for all, right? And then negation will go inside. Now if the negation goes inside, and again this conjunction then will become implication. So it will look like this. So this will become for all. This conjunction will become implication, and then negation of this part. So negation of this part again means this will become there exists, and here it will be the negation of this thing. Okay. So the quantifiers change. This there exists, and it's this for all. Say this there exists becomes for all, and then this for all becomes there exists. Okay. So when we say that z cannot be pumped, then we have to consider all breakup, because here there is a for all, right? So yeah, we have to be careful when we argue that some z cannot be pumped. And the same thing we discussed for regular pumping lemma also. And here you see, as I said, so you have there exists here So this I may depend on the previous variables which you have here. So just to give you an example, and just to show you the cases where people normally make some wrong argument. So we take this language 0 to the I, 1 to the I, 2 to the I for all I, and suppose our n is 5, so we take some z which has length at least 5, so here it's more than 5, it's fine. And so then we ask, can we pump this z? Okay, so let's consider this argument that we break this z into this 5 part. Okay, and then if we pump this, so this part is this v and this part is this x. So now if we pump this thing, you see we have a 0 1 0 1, and here we will have a 1 2 1 2. So this form does not conform to this form, right? So this sort of string is not in L. So can we say that okay, this proves that this z cannot be pumped? No, because again here now we have a for all, right? So we cannot just say that okay, we have one decomposition and for that we cannot do this part. So we need to argue it for all the breakups, that no matter how you break this up, if the breakup satisfy this constraint, okay, here the breakup satisfies this constraint. So you see that this VWX, so this together, so this is less than equal to 5, so this is exactly 5, right? So it satisfies this constraint, and Vx is obviously not empty. So these two extra constraint you have to satisfy, and then you will show that there is some I for which this is not in L, but that you have to do for all breakup, right, with this constraint. So but if we cannot argue that this z cannot be pumped using this this faulty argument, then does it mean that z can be pumped? Because we said that the case where we are showing that it can be pumped, so for that there exists is so we have a there exists, so just one breakup is fine, right? So then can we say that okay, so we just consider this one breakup, and you see that for I equal to 0 this is this. So why is it so? Because this v is this part and this x is this part. So you are putting this as 0, that means you are taking this out. So you have 0 0 1 1 and 2 2, which is in L. So then can we just argue that z can actually be pumped? Again no, because now here so when you are trying to prove that something can be pumped, so then you have a for all here, right? So if you are trying to prove that something can be pumped, here you can take any breakup, but here you have to prove this for all I. When you are trying to prove that something cannot be pumped, then you have to consider all breakup, and then just any one I will do here. So either of this thing will have to be there. So both of these arguments are faulty. So what is the correct argument and what is the correct answer? So in fact z cannot be pumped, and this we can argue by considering all the breakups, and we can classify these breakups into 3 cases. So you see that the first case I consider is that this v or x, So v and x are substrings here, right? So this whole thing is UVWXY. So I'm considering first the case where this v and x consists of one symbol. So I mean the v cannot be, say, this, like consisting of 0 and 1. So or this x cannot be 2 symbols or 3 symbols. So the first case is both u and v consists of just one kind of symbol. So if that is the case, so for example, if I take this sort of breakup where this u is just this part and x is just this part, so then you see that if we pump this string, so this type of strings will grow in number, right? But we have 3 types of strings. So if I just increase the number of 2 types of string here, so then it will not match this equal number of strings format. Okay, so we cannot pump in this case. So the next case is that this either v or x involves 2 symbols, and 2 symbol means they span this boundary. So here we have a boundary from 0 to 1, and here we have a boundary from 1 to 2. So at least one of this thing, so both of them do not have to satisfy this, at least one of them satisfies this condition that they involve 2 different kind of symbols. So either it is 0 and 1 or it is 1 and 2. But then if we pump this thing, so we are pumping both v and x, so then we will have this sort of thing. So for this 0 1, we will have a 0 1 0 1, and that will violate this structure. Or for a 1 2 sort of thing, we will have a 1 2 and 1 2 like this. So this will violate again this structure. So we cannot have 2 different symbol in v or x. So in both these cases we cannot carry out this part. Okay, and then the remaining thing is that this UVX consists of 3 different symbols. But then since we have chosen this n to be 5, so here the only possibility is that it has to start from here, and it must end here. So the only possibility here is this. In a general case you can have other possibilities, but here also we cannot pump. Okay, so again, why we cannot pump? Because we already excluded these 2 cases. If we exclude these 2 cases, so then the only possibility from here is that this entire string is either v or x, and the other 2 parts are epsilon epsilon, right? So again here we cannot pump. So for all the cases, so these are all the possible cases. So we saw that we cannot pump it for all I. There exists I. In fact, for I equal to 2, it will break. So yeah, for I equal to 2, it breaks for all these cases, and hence Z cannot be pumped. So if we formally write it down, what is the pumping lemma for CFL? So L is a CFL. If L is a CFL, then there exists a N which only depends on L. Okay, such that any string in L which is of length greater than or equal to N can be pumped, right? So if L is CFL, there exists N such that for all string in this L such that this length of Z is N, so this part will happen. What is this part? It says that it can be pumped. That means there will exist this component UVWXY such that Z is the concatenation of this thing, Vx is not empty, this length of this VWX is at most N, and for all I, this pumped up version will also be L. So this is a formal statement of this pumping lemma. And so in contrapositive form, what will happen? So in contrapositive form, the negation of this whole part will imply that L is not CFL, right? So that is the contrapositive form. If you have some A implies B, so the contrapositive of A implies B will be negation of B implies negation of A. So negation of this whole thing is this big mess, which implies that L is not CFL. And then here what is happening? So this there exists will become for all. This for all will become there exists, and then this implication will become a conjunction, and then this there exists will become a for all, and then this big conjunction. So this first three component we can take as this together, and then this last conjunction we can convert into implication, and then this for all will become there exists, and then this will become the negation of this, and this whole thing is the negation of this part, which now implies the negation of this thing, which is L is not a CFL. Okay, so again this is the formally written version of the contrapositive form of the pumping lemma for CFL. So both of these statements are equivalent, and this is what we use to prove that some language is not a CFL, because pumping lemma is almost always used to prove that something is not in CFL. I mean for regular language for CFL for CFL. Okay, so now we have stated this thing. Now how to prove the statement? First of all, let us consider a CFL, okay, a CFL L. So since this is a CFL, there exists some CFG, okay, and we showed that we can convert a CFG to a Chomsky normal form, CNF, right? So this Chomsky normal form. And what was Chomsky normal form? So in Chomsky normal form, the productions were of this form: either a variable goes to a single terminal, so there is nothing after this, this single variable goes to a single terminal, or a single variable goes to just two variables. Okay, so this was the restricted form of this Chomsky normal form. And also so here I mean it assumed that this this epsilon is not contained in it is not contained in L. So that doesn't pose any problem, because when we are trying to prove that some L is not a CFL, so we can consider this L minus epsilon. So that will be epsilon free, and if we can show that that thing is not a CFL, then adding a epsilon to that will not make it a CFL. So we can always, without loss of generality, when we are proving that something is not a CFL, so we can take this to be epsilon free. So this we can do without loss of generality, without loss of generality. So epsilon is not part of this language. Okay, and that is why we can have the CNF where all the productions are of this form. Now, how does a derivation tree look like in this CNF grammar? See, all the internal nodes are variables, and this branching corresponds to a production, right? So that means this is a variable which where we apply this sort of production. So if this is A, then this will be B and this will be C, and all the branching are of this form. So one variable is broken down into two variables, and at the very last step, So these red dots are terminals. Okay, so these blue dots are variable. So all the leaves are terminals, right? So in a derivation tree, the leaves are precisely the terminals, and since we are taking CNF, there is no epsilon production, and so there is no epsilon in this red dot. So these are just terminals. And so when can we have a terminal? So we can have a terminal only through this sort of production. So a single variable expands into a single terminal. So we just have a one-to-one correspondence here. So this is what a derivation tree looks like for CNF grammar, right? So now consider this tree and say the number of leaves is n. Now what is the number of leaf? So this leaf, so this is the yield of this tree, right? You remember we defined this yield and all those things. If you forgot, then just go back to those slides. And so if we take all these symbols here from left to right, okay, that is the yield of this tree. So if we concatenate all these terminals, these are terminals. So that is our string, the string that we are deriving through this derivation tree, right? So that is the string, say W. So that means the number of leaves here, so that is the length of this string. Okay, so the number of leaves is precisely, the leaves are precisely the symbols of this string. So the number of leaves is the length of this string n. And also say the height is h, right? Now if we just remove these leaves, this red dots from this tree, okay, and construct this new tree, okay, this is not a derivation tree of W, but we took this derivation tree and we just removed this last part, this leaves, okay, and then we got this thing. First of all, what is the number of leaves here? So here we have this variables as leaves, but the number of leaves doesn't change, right? Because here we had a one-to-one correspondence. So you see that we chopped this down, but still we have this here. So the number of leaves here is exactly equal to the number of leaves here, right? So still we have the number of leaves as n, but the height got reduced by 1, because what is the height? So it's the length of the longest path from this root to some leaf, right? So in this case we can take this, so 1, 2, 3, 4, 5, and here every path to this leaf is shortened by 1 because we are removing this last step. So whatever was the longest path, say in this case it was 5, so now it became a path of length 4. So now the height got reduced by just 1, right? Fine. So now this tree here, every internal node has exactly 2 children, right? Because of this it has this property, and this is the same here. So each internal node has exactly 2 children. So that means what is the we can put an upper bound on the number of leaves here, right? So if the height was 1, so then you can have at most 2 nodes here. So if you are considering height 2, so say this and this, then you can have at most 4, because then this 2 will expand into 2 and 2, right? So after this you can have say 8. Here we do not have 8, but at most you can have 8 because each can double up, right? So if you have a height h minus 1 for this tree, so that means the number of leaves that you can have here is at most 2 to the height of this tree, which is h minus 1, right? So we have this upper bound on the number of leaves here. So it is less than 2 to the number of height of this tree, which is the height of this tree minus 1. So that means we have this inequality. The height is at least log base 2 of n plus 1, right? Because height is a integer obviously, and here you see that h minus 1 is yeah. So what we can say here is that if we have any string in this language L, okay, so then in this grammar that we are considering for this L, height of this derivation tree of W for any W, the height satisfies this lower bound, okay, log base 2 of the length of the string plus 1. So this is what we have for any string in this CFL L. In fact, it would be easier if we use Z as a variable here instead of W. So the same statement for Z. So now we need this result in order to proceed. So let's just tabulate it here. So again we have CFL for this language the language is a CFL, and we have a CFG which is in Chomsky normal form. So this is important, and which is generating that language. And okay, again, so here I need Z. So for any Z in that L, the height of the derivation tree of Z is log 2 Z plus 1 at least. So now consider this set of variables and the number of variables. The cardinality of this is say m, which is the number of variables in this grammar, okay, and then consider this n, which is 2 to the m, okay. So m is the number of variable and n is just 2 to the m, so that log of n is m, right? So that means if I take any string Z in L, okay, such that the length is at least n, then the height of the derivation tree, okay, in this grammar, whatever grammar we have fixed. So in this grammar, the height of the derivation tree of Z in G should be at least should satisfy this inequality, right? So if this the height is h, then h minus 1 is greater than equal to m. That comes from the previous discussion that we have here. So this is at least this thing. So h minus 1 is at least log n. So yeah. And so now if this h minus 1 is at least m, so then consider the longest path, okay, from root to some terminal. So whatever the height is if it is h, so then there exists at least one path which has length exactly h from this root s to say a terminal. And then this terminal is part of this string Z, right? So this entire thing is Z. This entire thing is the derivation tree for Z, and there is some terminal such that the path up to this root is of height h, which is which satisfies this thing. So now again, like before, we just discussed this last part. So here we have just one-to-one correspondence from a variable to a terminal. So you just discard this last level and consider up to this part. So from here to here it is h minus 1, which is at least m. And since from here to here it is at least m, so starting from this bottommost variable, you just go up to the point where it hits m, okay. So it is at least m, so you can go up to m. So this can reach s also, but it can stop before, right? Because this can be more than m, but wherever m stops, you go up to that point. Okay, and consider all the nodes here. Okay, now from here to here, this part, so if this has length m, so that means here we have this m, at least m plus, so not at least, so this is exactly m, so here we have exactly m plus 1 many this blue vertices. And what are these blue vertices? These blue vertices are variables, right? At the end, these red vertices are terminals, so these blue vertices are variables. So up to this point, starting from here, we have exactly m plus 1 many variables up to this point, and there are only m many distinct variables, right? So that means there should be a repetition of variable. There should be some variable, say a, which is repeated at least twice. Okay, so that means there must exist a path from root to a terminal of length at least m plus 1. Why m plus 1? Because of this last part. So that means from here to here it is at least m. So if I consider the last m plus 1 symbols, so again this plus 1 is for this last part. So I'm actually considering the m length m starting from here and going upwards. So if I consider this, so this path must contain a variable twice. So this is the crucial part of the proof. So let's say this is the variable that occurs twice, right? Now if this is the case, see, starting from S, it got to this A, and then there are other branches going out from this part. So you have, it is a tree, right? So there are other things going in the left and right. So starting from S, you will reach something like this. So this A is here, and there is something before it, there is something after it, alpha 1, beta 1. And then starting from here, this A is expanded, right? So this A expands into these terminals, whatever these terminals are. So starting from A, so now I'm talking about this tree. Okay. Now when doing this, so up to this point, it was alpha 1, A, beta 1, and then this A, whatever A was here. So whatever A was here, starting from here, now you have another A, right? And again from here, this A expands into something, and so from here, so if you consider this A, again from here you have something going in the left, something going in the right, in multiple part, whatever. So you have something in the left of this A and something in the right of this A. So this A expands into some alpha 1, A, beta 2, right? So this A is this A. This A was this A, and this A here is so this A is this A, and this one is this one. So these two A's are this one. Now this A, okay, so if this A expands into this one, so up to this point, so then okay, if I put it here, so then from here I get alpha 1, alpha 2, A, beta 2, beta 1, and then finally everything goes to some terminal. So this A now goes into, say, this W, and this alpha 1 goes to U, this alpha 2 goes to V, beta 2, beta 1 goes to X and Y respectively. So if I match it with this one, so you see that S goes to this thing, and then this alpha 1 and beta 1, they go to U and Y, right? So starting from here, it got to this A, and whatever was in the left part, so this was this alpha 1, which ultimately went to this terminals U, right? And whatever was in the right of this A, so all of this went to this Y here, right? This as this beta 1, so this Y. And in the middle, so this A first went into this alpha 2, A, beta 2, where this alpha 2 and beta 2, so they correspond to this part, and this part, so this alpha 2 beta 2 finally expands into v and x, and then this a, so finally this a, so this a just expands into this w, right? So this is this u v w x y. Okay, I hope this is clear. So now first of all, you notice that both v and x cannot be empty, right? So if both of them are empty, so then you see that this alpha 2 beta 2, so they goes into v and x. So now if v and x are empty, that means we have a going into a in multiple steps, right? So this derivation happens in non-zero many steps. So that means we have to have a unit production which is not present in Chomsky normal form. So you just go back to the Chomsky normal form, and you see that we took a lot of pain in order to remove this unit production and those sort of things, epsilon production. So in fact there is no epsilon production, so we don't even need this argument. So we can readily say that this cannot happen because, but for that we need to argue anyway. So since we are doing this for both of this thing, so this is one valid argument. Okay, so this cannot happen because we do not have any unit production in CNF grammar. So that is why Vx both cannot be empty. One of them can be empty, obviously. And then you see that starting from here, if I have this derivation for this string, then I can also guarantee the existence of other derivations for other strings. How? Because we take up to this point, this is fine, so this part is same, and then this a, instead of expanding this a into this w, we can again use this, right? So now from here, using this, we have another alpha 2 and another beta 2. We have alpha 2 square, beta 2 square, and again we can use this. So then we will expand this into alpha 2 a beta 2, so we will have a alpha 2 cube a beta 2 cube. And if we do this I many times, we will have alpha 1 alpha 2 to the I, a beta 2 to the I, and b1 here, beta 1 here. So then finally we can use this alpha 2 and beta 2. So for this alpha 2 and beta 2, we can use this x and y. So okay, so all of them should be star. So this should be star, this should be a star, and these are this is also a star. Okay. These are all star. So this happens in multiple steps, right? So these are all star. This is also star. So this is also star here. So this is how we see that we can generate this UVI WXIY, which was required, and we also proved that this part is non-empty. So the only remaining part of this pumping lemma is that we need to show that the length of this part UVX, so from here to here, so this should be at most n, and for that you just see that we consider up to this length m starting from the bottom, right? So this is what we have, we considered up to this length m, and within that we were guaranteed to have this repetition of a's. So if I consider this and just take the height of this part, okay, starting from here to here, so the height is at most m, right? Because this part is at most m, so this is not more than this, so the height of this part is just m. So now if you consider this subtree, okay, so in this subtree also, by this CNF rule, all the internal nodes have degree exactly 2, right? So if all the internal nodes has degree exactly 2 or 0, if it is a leaf, then it has degree 0. So then this part can't be more than 2 to the height of this part, okay? So the height is m, so the base here contains at most 2 to the m many nodes. And at the last part, so we just have so a variable is just converted into terminals. So at this part, the coordinate digit doesn't change. So the yield of this part is just concatenation of VWX. So from here we have VWX. So length of this is just bounded by this 2 to the m, which is n. So this was the remaining part, which we, and so now we are done with the lemma. And now we just demonstrate how we use this pumping lemma to show that something is not a CFL. And it is very similar to what we did in regular language. So again, we take this language 0 to the I, 1 to the I, 2 to the I. So this part, so for all n, we have to show that this thing goes through. So we say that let n be a pumping lemma constant. So we cannot take any specific value for n because we have to prove it for all n. So just let n be n and call this pumping lemma constant. And then we choose a z. Okay. So if you can take any z and go through with this part, then this will be proved. So we have to choose this carefully such that z cannot be pumped, because we are trying to show that it is not a CFL. And the number of cases where we so here, right, so the number of cases should be minimized, and we discuss this in detail for regular language, why it will matter. So now if we take this and if we take a z and this breakup, so we consider all breakup with this constraint that they both cannot be empty and this part should be at most n. So then from this choice you can see that this VWX cannot have 3 different symbols, because in order to have 3 different symbols it has to go from this 0 to 2. So it has to include all the ones. So then the length of that thing will be more than n, but it cannot happen because of this constraint. So that is why I say that this number of cases should be minimized. You should choose z in such a way. So if I chose this to be say n by 2, n by 2, n by 2, then also this will be more than n. But in order to argue that z cannot be pumped, so we have to consider another case where this VWX contains all 3 symbols, but that is eliminated since we chose this part, this z. So now, as I argued before, you just consider the 2 cases where this UVX they consist of just one type of symbol, or they consist of 2 different type of symbols, which can be either 0, 1 or 1, 2. And in both cases, just for I equal to 2, you can see that the string cannot be pumped. So this is satisfied. And then you argue that this is not a CFL. So just one more example. Again, you take this consists of just one symbol, but you are taking 0 to the something which is a perfect square, and you are taking all the perfect squares here. So again, you just choose this z, which is in this language and whose length is at least n. So we are taking n square, and then we are considering all breakups with this constraint that Vx cannot both be empty and this part should be less than or equal to n. But then since we have just all zeros, so all these u, v, w, x, y, so they are just zeros, right, with some number of zeros. Now, so if you take this v and x together, so that means you are talking about b plus d many zeros, right? So this b plus d is greater than or equal to 1 because of this constraint, right? and this translates into the fact that if you take b plus c plus d, so that is at most n, right? So this means that b plus d itself is less than equal to n. So this b plus d is strictly greater than 0, but b plus d is at most n, right? So then if you just consider this v square x square, that means you are introducing one more v and one more x. So that means you are introducing b plus d many more zeros. So 0 to the b for v and 0 to the d for this x. So you are introducing, so we already have this from this, and here we are introducing this thing. And now you can see that if this is at most n and it is strictly greater than 0, then n square plus this thing which is here. So this is not a perfect square. So that means this string is not in L. So we have this. So that means this L is not a CFL.